Hello, my name is Bob D. Hilster, and I am your particle model guru. Today we're going to follow on with looking at parallel resistors. We're following on from my previous video, which was titled Battery and Resistor. So I'm going to continue that circuit, but this time the first resistor, the 8 ohm resistor that I used previously, is replaced by two parallel resistors. R1 and R2 are considered in parallel, R3 in series, powered by a battery. Okay, now you can look this up and you can derive this equation or read it. It's not complicated. Not my intention to go through all that. And so the value of that parallel resistor is R1, R2 over the sum of R1, R2. But the main point here is that there is the total value depends on both resistors. Each resistor must adjust the flow of G1s in itself based on the value of the other resistor. That's the strange thing. And if you look up the link, almost any link, and I looked up several, they all jump right into the derivation of the equation. And that doesn't help explain anything about how it works. So how can R1 know the value of R2, or how does R2 know the value of R1? Resistors can't know anything. So somehow this works, but they don't. They can't. They don't know anything, and modern science has no answer in terms of physics. Yeah, they got an equation. The equation works. Yeah, I know it works. I've worked on electrical circuits for 40 years. Just as a review, way early in my presentations, I introduced the idea that there's two gravities. You can watch that video. And I keep suggesting that around every object, around me, around you, around those resistors, there is a net force field. There is a gravity 1 field around it, and when you have a gravity 1 field, it builds up a net force field. There is a gravity G2 field of particles around it. It does exactly the same thing. It surrounds both resistors, which provides a net number of G2 particles to move the G1s out of the resistors. That's a hint as to what's going on here. So let's take a look at this. This is I find this a very interesting drawing. Yeah, I did it. I'm going to compare the performance of a copper wire, which I have previously discussed in terms of a magnetic field, and a resistor where a continuous flow of G1 particle is moving through the copper wire and through the resistor. Now, when you have a DC flow of what normally called DC current, what you have in the particle model is just a lot of G1 particles flowing through the copper and flowing through the resistor. And because of that, as the particles pass through the copper this way and these particles pass the other way, they set up force differentials. There's more particles pushing on this side, and then there's more particles pushing on that side. And that helps build this magnetic field. But the magnetic field doesn't just build itself magically. It always follows the left-hand rule. And I kind of draw that if you put your thumb pointing in the direction of this arrow and look at the direction of your fingers using your left-hand rule, you'll see that's the direction that the magnetic field is to flow. And it happens all the time, 100% of the time. And I have suggested in two previous videos that that's caused because of the organized atoms in the copper wire. When we make copper wire, we extrude it, we anneal it, and it all gets settled down nice, neat, and pretty. It's well organized. And when we do that, I've stated the one reason that this magnetic flow is always that way is because the G1 particle, while it's flowing through here, gets guided through such that it takes a spiral path. And it's that spiral motion that when these G1 particles, some of them escape, they're moving in a spiral path, and the G2 force field traps them and the magnetic field builds. That's what I've been suggesting for quite a while. And so you get a magnetic field here. But if with a resistor, the resistor in fact is deliberately built not to be organized. It's deliberately built to lose G1, so that there's an interaction that as the G1 flows through the resistor, that the higher the resistor, the more of these G1s get kicked out. They're built that way, which totally disrupts the possibility of getting this effect. And so even though some of the G1s are, maybe even a lot of the G1s are coming out because they're being scattered and pushed, they don't form a magnetic field because the G1 particles flowing inside are not moving in a spiral pattern. Not, at least not in a continuous enough one to support the building of a magnetic field around a resistor. Very interesting how these two parts work well together and can be explained using the particle model. Okay, so this is just a kind of a summary. In a copper wire, you have a continuous flow of G1 particles that helps build the G2 gravity field. You get the G2 field, no matter how they're flowing, as long as whether it's spiral or all mixed up, you get the G2 field. But in a copper wire or any other such structure that is well ordered, it causes the G1s to have a spiral path, and that allows the buildup of the magnetic field. In a resistor, you got the same thing to start with. A continuous flow of G1 particles helps build a G2 gravity field. The gravity field is there. Even though someone might argue, well, Bob, there is no magnetic field, so there's probably no G2 force field. No, my opinion, it's there. And because of the randomness of the resistor, randomness of the atoms, that prevents a consistent spiral path for the G1, consequently, no magnetic field. The concepts work together and help explain both left-hand rule, magnetic field, no magnetic field. Okay, so let's take a look at the parallel resistors. This is a rather strange drawing. Anyway, so we have resistor R1 over here. By the way, this does not mean one, that's an arrow. And this is R2. And I divided the resistors in half so that I can show in one effect, which is the scattering effect, and then there's the gravitational effect. It happens over the whole resistor. It doesn't happen this doesn't happen up here and this here. It's a continuous thing for scattering. It's a continuous thing for gravity pushing. But nonetheless, this is easier to show so I can separate what's going on. So you have G1 particles entering the resistors, and the interaction can be always be the same. It can either get pass all the way through, or it can hit another G1 or hit the nucleus and scatter, Here they're bouncing off, or they can get trapped. Trapping is not shown here. I use trapping mostly for electrostatics. Now the first element of losing G1s, because you have a voltage drop across from input to output, there's a voltage drop, and I contend that voltage drop is directly dependent on how many G1s are lost in any short interval. So, typically I showed before 1,000 in, 992 out, because 8 G1 particles were lost. Well, this is much more complicated. I have no numbers here. It's not easy to work out. So the first part is the scattering. That's a simple one I used in the previous one when they weren't parallel. You scatter so many, you lose so many, that's it. If I only had one resistor, if I only had this one resistor, 1,000 in, 8 get scattered out, and I have 992 out. That's a simple, straightforward effect of the G1s flowing through, and scattering is the way it gets the voltage drop. This is something else again. Now this shows the G2 force field. Blue is the G2 particles coming in this way, and G2 particles coming in this way. And as these pass through the resistor, they do the same thing. They pass through, they interact and scatter, or are trapped, but nonetheless they're lost. And there's fewer of them over here. Same thing with this way. We got G2 particles coming in, they're scattered or lost as they come through, there's fewer. That sets up a force differential. This number of particles is fighting against the smaller number, giving a net force to the right. And I show the G1 particles being pushed out of the resistor in that direction, as the same way here, it's being pushed out because this is gravitational. This is G2 gravity. This is just hitting and scattering. This force differential is based on the value of this resistor. The more resistance this is, the more loss. The more loss, the bigger the differential, the more the loss. That's the concept. It isn't that this resistor knows about this one, it's that the force field surrounding it the force field here is different than this force field. If in the case of trying to emulate an 8 ohm resistor, you use 12 ohms here and 24 24 ohms here, 12 and 24. You use their formula, that gives you 8 ohms. But since this has twice the resistance, there's more loss, and therefore this force is twice as great. And since this is only half the resistance of this one, the loss is half, and so the force is less here. That's how they know. That's what causes them to, in a sense, know what the other value is. Now there's a little bit of equations. I don't do this very often, but there is a term I've used since I started working on gravity 13 years ago called the interaction factor, and this interaction factor is a kind of a constant based on the idea that the percent reduction as the G1 particles pass through the resistor is proportional to the resistance in the case of a circuit, or in case of gravity, is proportional to the mass. Now at the very bottom, this is an equation that I used in my gravity equation. The percent, well, I got resistor here. I probably should have said the percent reduction as you go through the Earth is proportional to the mass of the Earth, and here is the constant. And I highlight it in red because I spent about 3 years ago, before we started on light and magnetism and the rest of it, the last calculation I did, I spent 6 months getting a preliminary value of this constant. I call it a virtual constant. Well, I have that value. I have a preliminary value. It's not been. I need to do more calculations in order to verify. I got to find other ways to do that calculation and verify the values. But you do the same thing in a circuit. The percent reduction to the circuit is based on the interaction factor as the G1s pass through the resistor, and it's proportional to the value of the resistance, and that's in ohms. So yeah, it's just in ohms. Now, in the case of the pushing, in the percent lost in pushing, it's a different function. Really, I really probably need to go back to this picture because there's the pushing effect is the G2 force field, and that's caused by G2 particles that surround this, and all the particles are coming at it in all directions, and then it's set with the copper wire there it sets up the field. And even though these G1 particles are pushing on the copper wire and pushing on the resistor, the organization of the G1s in this case is much different. This is like a stream of water going through a water hose, a high powered. It's organized as a solid mass of G1 particles just plowing its way through the circuit, whereas the G2 force field is the other way around. So the interactions themselves individually happen, but because the source is organized differently, I assume, and I go back all the way to here, I'm assuming that interaction factor is different because the source is different. But these are the types of equations I use, and you have to, in order to use my gravity equation and apply it anywhere, you have to know what these numbers are. But that's the way I get by using this, and this is just a supporting equation of the main gravity equation. Okay, so in summary, parallel resistors, the empirical equation for parallel resistors work. It's called it empirical because it's used from data. You measure voltage across the resistance, you measure current through the, and you can see that, oh yeah, every time you do it, it's this way, and so they play around with Ohm's law, Ampere's law, and they come up with that equation. It's an empirical equation, and modern science has no explanation. The particle model suggests that the overlapping G2 force fields around the resistor cause the flow of the G1s in each resistor to change according to the value of the other resistor. You can look up parallel resistors again. I don't care. You won't get a suggestion like that. Now, maybe I'm wrong because this is a very new model, but it looks very likely that this is what could happen. It's difficult to provide a simple mathematical analysis like I did previously with because there's so many variables. I'm going to go back, keep going backwards. Let me show you the variables. I haven't even talked about. Assume I have 1,000 coming in. They split. How do they split? Initially, they're going to split according to the mechanical connection. How many open paths are this way and how many open paths are this way. There's no guarantee that's 50-50. I've tried mathematical analysis with 50-50, and you can play around with numbers, and okay, you get something, but so you don't know how many are going which way. Although the G2 force field might actually affect how that happens. Anyway, then you've got the interaction factor of scattering in here as it's plowing, as this large volume of G1s are plowing their way through. Then you got the G2 interaction factor, and I don't know what that is. I may have an idea of what this is, but there's so many different things going on here making an analysis. So it's difficult to provide a simple analysis because there are so many variables that are not known. Yes, I have a lot of work to do. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.